Hello everyone, welcome you all to the second lecture of losses in pre-stress. In previous lecture we have discussed three types of losses. Continuing them in today's lecture, we will discuss the problems on those losses. So let us first take up an example in which we are considering loss due to elastic deformation. So given example, a pre-tensioned concrete beam of dimensions 150 by 300 is pre-stressed by using 8 high tensile wires, each has a diameter of 7 mm. The location of these wires is at 100 mm from the soffit, that is the bottom of the beam. So pre-stress is applied, which is of intensity 1100 Newton per mm square. We have to calculate loss of stress due to elastic deformation. The modulus of elasticity of steel as well as concrete are given. So let's start with the example. Firstly, let us find the total area of all the wires, that is pi by 4 into 7 square, which is the diameter of one wire, into 8, which is the number of wires. We get that as 308 mm square. Now as stress is given, we need to find pre-stressing force. We know the definition of stress is force upon area. Therefore force will be equal to stress into area. Given stress is 1100 multiplied by 308, which is the area of the total pre-stressing wires. So we are dividing it by 10 so that we can convert it into kilonewton. Now here the answer which is there is wrong. The actual answer comes here as 338.8 into 10 raised to 3 kilonewton. Again I am repeating, the value of P is 338.8 into 10 raised to 3 kilonewton. While solving this example in your notebooks, please make that correction. Next, area of the section is 150 into 300, which we get easily. Then moment of inertia is BD cube by 12, which we get as 337.75 into 10 raised to 7 mm raised to 4. Then here we need to calculate modular ratio, because when we have to find losses due to elastic deformation, we need to find the modular ratio. The notation for it can be simple small m or alpha e. Any notation you can use. It is the ratio of modulus of elasticity of steel to concrete, which is 210 divided by 31.5, which comes out to be 6.66. Now eccentricity, location of the beams is 100 mm from the bottom. As the depth of the beam is 300 mm, the CG or the center line of the beam lies at a depth 300 by 2, that is 150 mm. Wires are lying at 100 mm from the bottom. Therefore eccentricity will be 150 minus 100, which is equal to 50 mm. So next, let us calculate the stresses in concrete at the level of steel. Yesterday we have discussed the formula, which goes like this: P by A plus PE into E divided by I. Again I'll repeat, P by A plus PE into E divided by I. So substituting all the values, we get Fc is equal to 10.02 Newton per mm square. Therefore loss due to elastic deformation is modular ratio into Fc, which gives an answer of 6.66 into 10.2, which is equal to 66.73 Newton per mm square. Therefore the loss of stress due to elastic deformation is 66.73 Newton per mm square. So this much of stress from the applied stress of 1100 Newton per mm square is lost due to elastic deformation. So if we want to find in terms of percentage, we can find it, that is loss in deformation divided by applied stress into 100. we get the answer as 6.06 percentage. Therefore, we can conclude that here the losses in pre-stress due to elastic deformation is 6.06%. So let's come to the next example. Here we have a post tension beam. Okay, here we have a post tension beam of section 100 by 300. It is pre-stressed by using 3 cables. Each has an area of 50 mm square. The initially applied pre-stress is 1200 Newton per mm square. All 3 cables are straight and are located at 100 mm from the soffit of the beam, that is bottom of the beam. If modular ratio is 6, calculate the losses in the 3 cables due to elastic deformation for the following cases. First case is simultaneous tensioning and anchorage of the 3 cables. Second condition is successive tensioning of 3 cables. So most important point here is it is post tension beam, and for the following 2 cases we have to obtain the losses. So now firstly let us find force in each cable, because again the stress value is given, which has to be multiplied by 50, which is the area of each cable. Therefore each cable will have a pre-stressing force of 60 kilonewton. Area of the section can be found out easily, which comes out to be 3 into 10 raised to 4 mm square. I can be found out using the formula BD cube by 12. Eccentricity comes out again to be 50 mm, because the depth of the beam given is 300. Center of the beam comes at 150. Location of the wires is at 100 mm. Hence eccentricity is 150 minus 100, which gives out to be 50 mm. Now stress in concrete at the level of steel, Fc is equal to P by A plus PE into Y by I. Okay, so here when we substitute the values, we get Fc is equal to 2.7 Newton per mm square. Sorry, it is Pe into E by I. We get 2.7. Now let us come to case A. In case A, as all the wires are tensioned simultaneously, yesterday we have seen in our theory part that there is no loss in the pre-stress due to elastic deformation, as all the 3 cables are tensioned simultaneously. Now let's come to the case B. In case B, what is the scenario is cable 1 is tensioned first, next cable 2 is tensioned, and next cable 3 is tensioned. So when we are tensioning cable 1, there is no loss due to elastic deformation. Now when we go to tension cable 2, loss happens in the cable 1 due to elastic deformation, which is given by the relation again modular ratio into Fc. You see here again I am repeating, when we are tensioning first cable there are no losses, but when we come to tension the second cable, the losses start taking place in the first cable, which are again given by the same relationship modular ratio into Fc. Modular ratio is given as 6, Fc we have found out to be 2.7. Therefore loss of stress in cable 1 is 16.2 Newton per mm square. Now when we go for tensioning cable 3, there will be loss in cable 1 and cable 2. Therefore loss in cable 1 is again 6 into 2.7, that is modular ratio into Fc. We get the same answer, 16.2 Newton per mm square. And in cable 2, the loss is again same, 6 into 2.7, which is 16.2. Therefore total loss in cable 1 is 16.2 when cable 2 is tensioned, 16.2 when cable 3 is tensioned. Adding it up, we get 32.4. In cable 2, only the loss takes place once, When the third cable is stressed, that is 16.2, and in cable 3, okay, in cable 3 there are no losses. So this is an example where the cables are tensioned separately and not simultaneously, hence losses occur. Whereas in case A, as the cables are tensioned simultaneously, there are no losses. So this is your second example. Now let's discuss one more example in which we will consider shrinkage. First two examples we have discussed on elastic deformation. Let's discuss one more example where we will take in shrinkage into account. Okay, so given example says that a concrete beam is pre-stressed by a cable carrying an initial pre-stressing force of 300 kilonewton. The cross-section area of the wires is 300 mm square. Calculate the percentage of losses of stress in the cable only due to elastic deformation, only due to shrinkage, please excuse me, only due to shrinkage of concrete. First case is beam is pre-tensioned, second case is beam is post-tensioned. Elasticity of steel is given and age of concrete at transfer is 8 days. Okay, so hope you recall yesterday's formula. So now let's start. Let us find initial stress in the wires. Stress is force upon area of the wires. Force applied is 300 kilonewton upon area of the wires is 300. We get an initial stress in wires as 1000 Newton per mm square. Now, if the beam is pre-tensioned, the total residual shrinkage, yesterday we have written directly, it is 300 into 10 raised to minus 6 or 0.403. 0.00003. We have written it. So here it is taken in terms of 10 raised to minus 6 as it goes easy for calculation. Therefore, now this value we can take directly as per the codal recommendations. No need to worry about this 300 value. Therefore, the loss of stress is 300 into 10 raised to minus 6 multiplied by the elasticity of steel, which is 210 into 10 raised to 3, which comes out to be 63 Newton per mm square. Therefore, percentage of loss of stress is loss in stress divided by initial stress into 100. The loss of stress was 63. Initial stress in wires is 1000. When we multiply it by 100, we get a loss of 6.3%. Now, in case of a post-tension beam, again this formula we have written yesterday. The formula is 200 into 10 raised to minus 6 divided by log to the base 10, 8 plus 2, which gives an answer of 200 into 10 raised to 6. Here 8 is the number of days or the age count at the transfer, which is 8 in this given example. So we get an answer of 200 into 10 raised to minus 6. Therefore, the loss is this multiplied again by the value of elasticity of modulus of elasticity of steel, that is 200 into 10 raised to minus 6 multiplied by 210 into 10 raised to 3, which comes out to be 42 Newton per mm square. Therefore, in case of post-tension beams, the total loss due to the shrinkage of concrete is 42 Newton per mm square. Therefore, percentage loss is again 42 divided by initial stress, which is 1000, multiplied by 100, comes out to be 4.2%. So here we can see that if the beam is pre-tensioned, we are getting a loss of 6.3%, whereas if the beam is post-tension, we are getting a loss of 4.2% of the given stress. So these three are just the practice examples which will be helpful for you all when we solve the further examples, and which will make you clear how exactly the losses have an impact. Okay, this 4%, 5% are quite considerable values, hence it also highlights the importance why the losses have to be taken into consideration by a designer. So in the next class we'll discuss the further losses with their relative examples. Thank you.